Yay!
Yay! Here's a quick little problem that pops up from time to time called like an out and back problem. It's like a boat that goes with the current and then against the current. So here's the idea. Suppose I got a little red boat, and let's say that the boat travels at 10 meters per second relative to the water. So if the boat has 100 meters to go, what you might imagine is that normally you would take 10 seconds, right? Because what you'd have is delta x is v delta t, right? One of our simple kinematic formulas. And so this means that the time taken is just the distance divided by the velocity, right? So if it's 100 meters divided by 10 meters per second, it sounds like it ought to be 100 meters divided by 10 meters per second. You ought to be 10 seconds for the trip. Now the complication is, suppose there's a current. So the way that I have it drawn here, maybe the current is going to the right at 5 meters per second. So then relative to the ground, so the thing is 100 meters away relative to the ground. So relative to the ground, the current is helping you on the way out. So you're going 15 meters per second on the way out, and then you're fighting the current on the way back. So you only go like 5 meters per second on the way back. Well, the reason that this is at least a little bit interesting is that, I mean, naively, you might say, oh, well, I'm having 5 added one way and then subtracted the other way, so it all sort of comes out in the wash. So really, the current doesn't make any difference, right? It should take the same amount of time. I should get my, for the whole trip there and back again, if there's no current, we said that it was 10 seconds, right? So with the current, is delta t equal to 20 seconds for the out and back trip. And again, naively, you might think, oh, well, we're adding 5 and then taking away 5, so really, the current's not really doing anything. It's not making any difference. Okay, well, let's actually figure it out, because it's a little bit interesting. Okay, how are we going to do it? All we're going to do is just use this simple formula, right? So the total time taken is just going to be the total time going to the right and then going back to the left, right? With the current and against the current. So the total time taken is just the total time to the right plus the total time to the left. And we can write those down. That's just delta x over the speed going to the right, plus the same distance divided by the speed taken to the left. So this is just going to be 100 over. Okay, now I got to be careful. So how fast are we going to the right? Well, we're going 15 to the right. Again, I'm leaving off the units. I'll stop remarking on it and just keep doing it, just because it makes things a little easier to read. So that's 100 divided by 15 going to the right. And then going to the left, we got 100, what's our speed to the left? 5, right? So if you actually put these numbers in, 100 divided by 15, that's like 6.7 plus, that's like 20. That's like 26.7 for the round trip. That's longer than you would think, naively, if you didn't think the current made any difference. So 26.7 is the time for the entire trip, maybe a little bit longer than you think. So why is that? Why does it take longer? And you probably are way smarter than me, and you already know the answer. And the answer turns out to be, we're looking at time, right? You aren't spending much time going to the right because you're going fast. So it doesn't take as long. But you spend a whole bunch of time going slow because the current is fighting you. That's why it's not exactly equivalent, because we're doing distance and not time. So the time taken in those two trips is not the same. Even though you're adding 5 one way in speed and subtracting 5 the other way, the time taken is not the same. So that's interesting. Let's solve it in general. This is something that we like to do in physics. In general, let's get sort of a general formula so we can kind of see what's going on. In general, the total time taken is going to be, well, we have it written up there, right? The delta x over VR plus delta x over VL. Let's factor out the delta x. And this is going to be 1 over VR plus 1 over VL. Let's simplify that a little bit. Well, let's just write down that's going to be delta x 1 over... Okay, let's introduce this. This is going to be the water. That's going to... Oops. Yeah, that's fine. Let's just call it W. I was going to call it V sub W, but that's too many letters. So that's just going to be water, the speed of the water. And the 10 meters per second, that's the speed of the boat, right? So V right is V plus W. And then this is 1 over V minus W. Right? So we can do that. But now, this is delta x over... All right. That's kind of a complicated looking combination of fractions. So one thing that we do over and over again that you might remember from algebra is if I want to combine, those denominators are not the same. So if I want to combine them, what do? I sort of cross multiply and then on the top, and then I multiply the bottoms. So it looks like this. So up here I've got V minus W plus V plus W on the top. And then on the bottom, I multiply those two denominators. Does that sound right? So that's going to be V plus W times V minus W. If you do that out, that's an interesting thing. V squared minus W squared. Right? And then look up top. I've got a V plus V, that's 2V, and a minus W plus W. Well, those just cancel. That's neat. So what I've got up here is I'm going to have 2V delta x over V squared minus W squared. Okay, in sort of formula form, that's what the answer is. And then what we do a lot of times in physics is you look at the limiting cases. So suppose there's no current. That's sort of the easy case. So no current, W equals 0. And if you just look at that for a second, if W equals 0, I've just got 2V delta x over V squared. Well, that's just going to be delta t is then just going to be a 2 delta x over V. That checks out. That's what we expect. That's what that was our naive answer of 20, right? 2 times the distance, because it's out and back, divided by our speed. That checks out in that limit. And then the other interesting limit is, look, in the denominator, I got two things subtracted from each other. What happens when W is almost equal to V? That thing is getting close to 0 then, right? It sort of blows up in a mathematical sense. You're dividing by something close to 0, and so the time goes way up. Well, that makes sense too. Delta t approaches infinity if the speed of the current is about the same as the boat. Because what does that mean physically? What that means is, look at that return trip. If W is about equal to V, so if your V is like 10 meters per second, and then the speed of the current is really close, like 9.9 meters per second, it means you almost never get back, right? The time coming back is going to be enormous because those two speeds are almost equal. And then if W is greater than V, well, then you get sort of a nonsense negative answer for T because you never get back at all, right? The current just keeps taking you further away. So this is so far our first example of getting a formula or sort of an equation for the whole system and then just taking different limits to make sure everything makes sense. So we'll do a whole bunch more of this as we go on. But that's sort of an interesting little problem that maybe isn't quite what you naively expected at the beginning.